Okay, please.
Okay, in the last class, you remember I was introducing some main concepts around methods for estimate parameters. I don't know, maybe we need to refresh some main concepts, but remember that this one. Remember that we focus on, we have a sample, always size n, and this is standard notation, and focus in this one, a family. Okay, I put this notation to do emphasis in a set of densities, probability density functions, attempting to model some pattern of uncertainty, okay, when the parameters are unknown, okay? You remember this is the main approach. Then we focus on to translate the uncertainty in a sample to constrain the parameter, the space of the parameter. Then the first one is to fix some solution for this parameter, to put some estimation, punctual estimation. And secondly, we can compute some interval. For instance, if we consider one dimension in the parameter, then we can consider an interval. But in more general case, we can fix theta living in a space of parameters with high dimensional, and then you take this idea of region in order to show some uncertainty around the capabilities of a sample to fix the value of the parameter, okay? Then that we can do always is using a sample to compute punctual estimation, and many times we can compute some region where live this parameter, okay? Always when we do this one, we can compute punctual estimation with different methods that I can comment today. And in order to, when we try to fix punctual estimation, of course, we can measure in some sense, which is the error. And based on some assumptions on the error, we can compute some regions, okay? The more typical one is confidence interval. And this is the more typical case when you fix more than region, you fix an interval, and we say confidence interval based on some risk that typically we denote by alpha, and then 1 minus alpha correspond to the probability such that our parameter live in the region or in the interval, okay? This is I tried to change. Sorry, I lost my screen. I lost the screen, sorry. You can see my screen?
Yes, the first slides.
Sorry. I don't know why. You see my slides?
Yeah, the first one, the first slide.
Okay, I put again. Okay, I continue.
Yes, no, okay.
Yes, okay. Then
first estimates, the first.
Yes, the first method for estimation, the most typical one is less squares. You remember that I was comment, and I am going to explain with more graphical example, which is this procedure. But let me to introduce methods, these main methods on moments and maximum likelihood estimation, okay? I suppose you have some probability background. Maybe not.
Yes,
then,
they have.
Okay, then it's so easy to introduce this method so quick. And moreover, some ideas on how to measure the efficiency and another properties around to decide which is the best method for each case, okay? Basically, when you want to measure or you want to decide which is the best method, you need to compute some distribution of low from the estimators, okay, for estimator as a new random variable that you produce with some observations. And then this law for the estimator can hold some properties like invariance or sufficient efficiency. And these properties really are very important from uncertainty point of view. And to measure each of one many times is from probability point of view is easy to describe, but from statistical modeling many times it's so difficult. And in practice point of view, you need to do that you can do, really what is the best. Okay, you have to put this one in your bin, because really, for instance, consistency of estimation is very important property, because it's related with normality in asymptotic sense. That this one is very strong result, because when you have some procedure for estimate such that when the sample size increase, the behavior of the uncertainty of the estimator tends to normal distribution, then you can use central theorem, and then you can show some strong properties around mean square error and etc. I have to remark that in many models from data science, we assume in some sense this property, but really it's not true from mathematical point of view in general. But many times we use that, we suppose that some good behavior in many points in order to can use this one and use mean square error, for instance, and as a good measure for the modeling of some statistical procedure. But really the math constraint to apply it is strong, and many times you need to review it, okay? And in this part I need to explain so quick, because I think maybe it's interesting to introduce some statistical modeling in more details. And this is more related from probability part, okay? Okay, the idea of method of moments is very easy if you know probability, no? Because when you have some set of observation, quickly you can relate with, you are observing a random variable, and moreover it's easy to be thinking that, okay, if this observation x1, x2, xn is based on some sample, then I assume that are independent and I are identically distributed. Then when I have really some different observation of the same random variable, no, and independence, strong properties I can use. One of them, for instance, is to measure the expected value of the random variable through the sample and to obtain good results in order to describe the uncertainty with a sample, okay? Then you imagine in your minute, you need to describe uncertainty of a sample. Then when you translate in math language and you say random variable, you know some properties, for instance, the expected value, and you know how to compute this expected value. You know some strong results in order to measure this one, and then you can conclude with some strong properties, okay? But more general than this one is to use another moment, okay? This one is, you can see expected value is the first moment from probability point of view, but the idea is to use several ones, okay? Remark that when you want to compute, for instance, the first one, this parameter, you know that in a regular case, if the one with the knowledge around this parameter is really going to describe very strong properties of the random variable, and consequently, you are going to describe uncertainty of the sample, no? And how you can describe this one? Everybody in general, if you was working in probability fundamentals, you know that a good estimator of this parameter is the mean sample, no? Then you can see that if you want to obtain a definition of the best estimator, in this case, you can obtain with less squared. Only if you ask which is the best point such that minimize L2 measure, no, the mean square, then you only need to derivative, no, and equal 0, and you obtain the formula of the mean. Then it's easy. And really it's very important point to remark, because really is the main definition of expected value, of the mean as estimator, okay? The mean as estimator. Okay, the idea of moments, I am going to pass so quick, okay, because there's more details around probability, but only remark this notation. When I put with capital letter, I describe the R moment, okay? And you can see it's not centered, okay? And when no capital letter, then it's centered, okay? This is empirical. Take into account that this is an empirical moments, okay? Because I have a sample and I can describe the R moment as the mean of the power R of the sample, okay? And in the same idea as to center moments, you can do the same. You can consider each observation centered by the mean of the mean of the sample, of course. Consider the power R, and then the mean, and at the end you have the moments, the center moments from empirical point of view. And remark that this one is from empirical point of view, okay? Then let me to pass so quick. Sorry, I want to pass because I want to remark the main points. And now you can see from probability, based on probability now, this notation, okay? Or if you want, you can consider this notation, this mu sub R for the R moment, okay? And if I put mu C, is a R center moment, okay? You can see that this definition is from probability. I don't need the sample, of course. I only need the probability density function. And this is the result of this. This one is really the definition of this one, okay? And the relation between, remark, that is from probability. I don't need to talk on a sample. Then you can see, let me to pass so quick, some details where you can see the center moments that you usually, maybe you work, are related with node center moments, no? Really exists some formulation and you can develop. And each center moment can be related with some set of center moments, okay? Really, it's important from a statistical point of view, this relation between different moments, because let to decide which is the best strategy when you want to use moments for fit parameters, okay? The basic idea to consider, sorry, I passed so quick, because now some properties that I suppose you don't need, how to compute moments of the random variable, okay? At the end, you can see you have some, from a sample, a mean related with the mu, the expected value. And another, for instance, a variance, no, related with the variance, the theoretical variance. And another one, in general, empirical moments related with populational moments, okay? Then, when you have a sample, you can compute this one, and with a theoretical model, you can compute another formulation. And now you fix that when I put this one, I am going to relate this expression. When I fix a model, a theoretical model, I am going to obtain an expression based on the parameters of the model. Then, with a sample, with a numerical sample, I am going to obtain some values. And with a model, I am going to obtain an analytical expression of theta. I say analytical expression because many times when we consider to use method, the moments method, is because we have an analytical expression. Otherwise, when I cannot compute an analytical expression of the expected value for a theoretical model, it's not too much interesting to use this method, okay? Then the main idea is clear, no? Because you only need to put equal in this expression and the other one, and then you can obtain which is the parameters, okay? Let me to put some details from a mathematical point of view that I am not going to remark too much. but only take into account that from the central limit theorem, you know that the expectation, the mean sample converges to expected value, then the expected value of the sample of the random variable, sorry. And using this one, we can extend in different ones because really the relation between the power is related, no, with the distribution of the variable when you consider power. Then in general, you can see you can extend from observe that I am considering no centered moments, okay? But remark that it's important from a mathematical point of view to take into account that the strategy of consider this one to compare empirical moments non-centered with populational moments can be used through center moments in here and in here, okay? And it's the same from the strong relations that I was showing. But usually it's more easy because you can see that from computational point of view to compute this one is very easy. Then when you have a strong data set, it's interesting to consider this one, only the air power and mean for different air. Then you have a set of empirical values that are going to attempt to describe really the uncertainty, and then you can compare with the law. You know that the law of a random variable can be described for all moments, no? Then this is the main idea, and important to take into account that this convergence from the limit central theorem that ensure that when the n increase, then the result holds, okay? Let me to show a small example. Sorry, because I have some animation, but when I am in a Blackboard, the class is presential, is so different. And then for me now, it's better to do it. You can see, it's a you can see it's with all details, okay? But it's important to take into account. This is the exponential family that maybe you know. This one, only one parameter, theta, exponential minus theta x, okay? This is the typical way to write probability density function related with exponential probability. Then to take into account if theta is unknown, but for instance, you know that has to be positive, then this one is a family and is a set, and you can fit theta using a sample, no? Then from theoretical point of view, you know that the expected value of theta, you can compute using the definition, no? Let me to show the details, but only you need to put the probability density function x, and then you only need to solve. And at the end, you are going to obtain 1 divided by theta, then this is the expression. And if you compute the mean sample, you only need to solve this equation, okay? Important. I have one parameter with only one dimension, no? Then I only need one moment, empirical moment, because only one parameter, only one incognite for to solve, then I only need one description of the sample. Then from here, you obtain that the estimator, a way to fit with theta is 1 divided by the mean, okay? Then this is an easy example with one dimension, and maybe it's interesting to fix, okay? Because typically we can to be some confused idea, for instance, in exponential model, because theta, I don't know if I have to put equal to mean or 1 divided by, and really, if the estimator of theta is this one, is because you use this parametrization of the family. And then you observe that I can use, for instance, another one typical to put no theta, I can put 1 divided by lambda is another typical expression for this model. Then if I put 1 divided by lambda, and in this one, 1 divided by lambda, and you reproduce this process, really, you are going to obtain that lambda is exactly equal to the mean, okay? Then is you can see, to do this one is very easy. It's very easy because, sorry, it's easy because you only need to fix the several moments in order to compare, okay? I am not going to show more details because with her, it's easy to fix. I really, the idea is easy because there are several books explaining a lot of details and examples, but it's important you know this method exists. And for me, I think the most easy is to take some package of R that are going to solve this equation, because many times if I have, for instance, no one parameter, suppose that you have 3 parameters, and you can suppose that the result are 3 equations with 3 empirical moments, and easily is non-linear relations. Then to solve with only 3, to solve the equations is not easy, and many times you need to do it with numerical procedures. Then this is the main reason that you have to know the procedure, but at the end it's better if you take a package. Okay, I saw it. As I was commenting, I want to talk on maximum likelihood estimation because really is the most important one from Fisher. Really, Fisher was one of the main statistical authors such that improve several results from practical point of view in statistical modeling. Of course, now there exist a lot of strong contributions, but remark that today with strong methodologies always are based on some ideas from this maximum likelihood estimation, okay? Then the most important one of maximum likelihood estimation is to fix that likelihood is a word that you can understand outside of statistical. It's easy that when in general, no, in science, when you say this is likelihood, is because you say it is something that is according to that you observe, no? And this is the main idea. From likelihood, versemblança in Catalan, I don't know in Brazilian, in Portuguese. I suppose it's something like versemblança. But maximum... Verosimil. En castellano, verosimilitud. Sí. Verosimilitud en castellano. But the likelihood is the most extended one. Okay. Likelihood, this method is based on likelihood. Okay. And to maximize the likelihood. But likelihood is a function. Okay. Then let me to introduce a function first, and then you see which is the method, because when I explain which is likelihood, that I am sure you know a lot of details, but let me to show in more general case, okay? Then you are going to relate easily with which is this method to fix some estimation, okay? In general, when I propose to use likelihood, we are thinking that you have a sample, and when I say sample are independent and identically distributed, okay? Then again, I have a sample, and I suppose that the samples is from some model, okay? And suppose that the model that you propose, remember that I say model because it's a probability density function or a probability distribution for a discrete case with some parameters that I don't know, okay? Then is a model, I propose a model, then I don't know the parameters I need to fix. Then which is the best way to fix this parameter? Then the main idea is this one, to describe likelihood, okay? Likelihood L is a likelihood and is a function of the parameters, and this is the main definition, okay? Is the probability, this equal is the definition, the strong definition. Now the next one I am going to explain, but the first one is the formal definition of likelihood. Likelihood of a parameter is the probability that you observe a sample. Okay, this is the definition. But to take into account that when I say probability to observe a sample is because you suppose, remember the first day that I was saying, when I say probability of a sample is because I suppose theta is known. Then the idea, the definition is probability of a sample when theta known is equal to the likelihood of theta when the sample is known. Okay, you can see really the definition is likelihood of theta is the function of theta when you know the sample, and it is equal to the probability of the sample when you know theta. Okay, this is the main definition. Of course, when you know that the sample is from independent and identically distributed, then this equal can be produced. For instance, for the discrete case. Okay, I show with a discrete case. Then from independence, I can separate with probability for each one, and from identically distributed, I only need to evaluate some law in each observation. Then the product of these probabilities is exactly the likelihood of this parameter. Then you can see if I change theta, this number change, then this is a function of theta, okay? But the sample is fixed because you observe a you observe a sample, okay? You observe a sample, then you are going to compute different probabilities based on to change this parameter theta. Then the likelihood is the main function in order to describe uncertainty modeling, and is extended, applied from a lot of in a lot of disciplines. I want to say that this equal is because are independent and identically distributed, but really is not necessary. I want to say the likelihood expression is this one, and really can be derived different applications from this one, okay? But the most typical one is this. When you have a sample, then you can do this second equal, and you can consider this one equal to this one, okay? In this case, you can see if we want, this function for the, this is for a discrete case is very clear. In a simplified when I'm considering independence and identically distributed, likelihood as a function of theta is really, if you want the likelihood with as a theta, as a function of theta, remember that x is fixed, and extend the definition from the discrete case to continuous case. Change the probability of a point, no, the probability of x equal x1 to density in the point. Maybe you can see that it's not correct, or maybe it's like an approximation, but let me to show a main idea around that. The most important one is this one. In a continuous case, you have to take into account that when you observe a point x, then when I observe a number, no, I can compute. If I consider theta is known, I can compute the probability such that my random variable lives in a small interval around this observation, no? Then the idea is, okay, I cannot compute in a continuous case x equal to x, but I can compute the probability of my random variable live in a small interval around x. And this one is the integral, okay? And the idea is to approximate this one for this one. So, and you can see this is the idea, no? That I can consider the density, the probability density function in the point as some approximation for the multiplied by the epsilon, no? The length of the interval as an approximation of this probability. Then with this idea, you can see that this epsilon can be removed and you obtain the definition that I showed, okay? This definition, okay? Then you can see this one, this idea that in a continuous case, we use, again, to approximate this one using this one, this epsilon multiplied by the density in the point. This is important to take into account because many times it's so difficult to understand how to can extend this idea of likelihood measure, likelihood from definition, likelihood measure probability, and always from practical point of view, we consider product of densities, okay? And you know that this one is not the probability of x equal to x, okay? It's clear that really This is not exactly computation, but it's close. And in order to fix a function for describe the uncertainty such that the uncertainty that you can translate in the theta from the sample is a good solution, okay? Okay. More typical one is to take into account that when I put this one, you can see this product from a numerical point of view show several complications. Then the most typical one is to consider the log likelihood that only to consider this application to take logarithm, okay, easily, and then you obtain this product transformed to sum, then not only from computational point of view, from many analytical description that you need to do, it's more easy and more clear, okay? There are several advantages in to be working in logarithm scale, but I don't need to remark now. You can see if you are working on that. But I only remark to my students that it's important to show that this function at the end, likelihood, are going to show some pattern like this one. And if I put function or logarithm of the function, the maximum, if exists, are not going to change, okay? Then the point when the theta point where the likelihood is maximum, when you obtain a maximum probability to observe the sample, is invariant if I take logarithm, okay? And with this one, you see, which is no, and now you can see, which is the method of likelihood estimation. Now, when I say we need to compute a method to fit a parameter based on likelihood, okay, you can see, which is the strategy to search, which is a parameter such that maximize this function, okay? Then another estimation method is based on maximum likelihood, okay? Is to search which is the theta such that are going to maximize the likelihood function. Remark that this point, the point such that is going to produce maximum in this function is the parameter such that maximize the probability that you observe this sample that you have, okay? Then maybe for you it's clear why you say likelihood, no? And from the intuition or the common sense, you can see it's a good method.
Isabel,
Yes?
they're asking what is the definition of argument, maximum argument.
Okay. This is it's no, it doesn't matter. It's to remark that we want to maximize L, but theta is the argument, this one. Because if you remove this one, typically you say the maximum of the function, and the maximum of the function is not important. We need to know which is the argument of the function such that maximize the function. Okay, it's for emphasis in this one is not the maximum value of the function. Is the argument of the function, okay? You understand? Arc is in order to emphasis in such that you are looking for, which is the argument of the function such that maximize the function, okay?
Yes.
Okay, then this is a definition of maximum likelihood estimation, and of course that I was commenting that you can remove likelihood in here and put log likelihood because it's more easy. And remark from computational point of view, it's clear that are going to obtain more easy procedure for to do it. And maybe it's important to remark this one. The model many times can be easy, but in general, the models, when you want to consider some constraint from practical point of view, like, oh, my data is round, or my data is truncated, or etc., then you need to describe the density with some strong analytical function, and then you need to set this maximum from numerical procedures, okay? Always you can see in the statistics and with large data sets, you need to recover some numerical procedures to really compute the results, okay? But let me show some example where you don't need to do it. Oh, sorry. I forget to put silence. Let me to show an example. Poisson, for instance, with a parameter mu. Suppose that you observe 7 times. You observe 1, 6 times you observe 2, 1 time observe 3, and 4 times observe 4. Then you can consider this frequency table. 1, 7 times, 2, 6 times. Then, okay, it's clear for you. Then when I want to remember, which is the objective is to describe the likelihood, okay? Remember the probability distribution. The probability of Poisson distribution is equal to K, is this expression, this is from model. This is a law if the parameter mu is known, but for us it's a model because mu is unknown and you want to compute, okay? You only have some observation. You observe this one and then you need to compute mu. Then what you can do, describe likelihood, and likelihood, you know the definition, you have to do the product of this one. And of course, you can see in this experiment, you do 7 plus 6 plus 1 plus 4 at the end, 18, I think, 80 times. Then n is 18. But 7 times you put 1, 6 times you are going to put 2, okay? Then it's more easy to consider this product with powers, no? Then, so let me to show. It's more easy to consider this one, this expression, okay? Likelihood based on this unknown parameter is some constant. Let me to fix that I put C in order to show that some constants, in this case, these factorials are going to be grouped in this constant, okay? For me, it's not important. And I am going to consider this one because it's a functional part of the law where I have the parameter. And you can see this one, when K is equal to 1, no? 1 observed 7 times. And 2 is observed 6 times. 2, this probability of the occurrence 2, 6 times. The probability that the occurrence is 3, 1 time, and the probability that the occurrence is 4, 4 times. And this is a likelihood. And why I put this one? Because it's not too much important, because at the end, for me, now I am computing the likelihood because I want to know which is the maximum from mu. And I can see from the expression that this constant is not important in order to obtain the maximum. Then it's tricky for simplify the calculation. And I recommend to be thinking some minutes previously to start to write a likelihood, because if you remove some complexity of the procedure, you are going to obtain more quick results, okay? Likelihood, you can see this is the expression. Log likelihood, remember, with non-capital L remark. Capital L is for likelihood and log likelihood. You only need to translate this one from logarithm, and then it's more easy expression, you can see. And with this expression, simplified, is this one, okay? You can see. C plus, this part depending of mu and mu. Then, now what I need to do to compute the maximum of the parameter, which is the maximum of the function, because I need to know which is the parameter such that obtains or hold the maximum. Then I compute the L prime, I divide from, this is a derivative from the parameter, very important. The likelihood, if I want to obtain the maximum of this parameter, I need to do the derivative from this parameter. Be careful, because many times we need to mix in some theoretical develops, we need to mix K and values of the random variable with parameters of the model. And many times it's typical to do some error when you have to do the derivative, okay? Be careful with this part. At the end, you can see you do the derivative from the mu, and this is the result. Then maybe it's interesting to fix that the derivative of livelihood from the parameter is the score function, very unknown. I don't know, maybe you see, or you are working in some results based on score function. Score function is famous from data science, score function, because it's related with the derivative of the livelihood. And livelihood in data science is very important, but not with this number, with this name, sorry. Then this expression led to describe which is mu, no? And in our case, mu is 2.11. Then this is estimation, a punctual estimation of the parameter. Then you can see I have an experiment, I have some data, I have uncertainty of the data, and translate this uncertainty to fix a parameter. Of course, now I can see if I want to do an interval, I have to continue with the computation. But now I am not going to focus because I was interested in to talk about one estimation of the parameter, okay, as a punctual estimation. But you can see now, maybe you are thinking, okay, and now the uncertainty of the sample can be translated to uncertainty of the estimation with an interval from this value. Because, for instance, maybe you see these results and say, oh, maybe I can put mu equal to 3. I can put 3. And with the result, this one, from a statistical point of view, the answer is 2.11, but the answer is not going to say this is exactly this value. Only say that this is a more probable case, because this is a maximum likelihood estimation, but an interval around this value is interesting to compute, because maybe 3 is one of them, one of the probability possible, one of the probably values for the parameter, okay? For instance, in this case, you can see the likelihood function. This is the graphical, this one is likelihood and mu, okay? And the maximum is in this point. The maximum you can see is in 2.11, is in this point, but the value of the likelihood you can see is around 16, no? Then really you can see numbers like 2 or 2.3 are likelihood too, no? Because really it's very pattern here, are very close to this point. Then one option to produce an interval of uncertainty around estimation is to fix some limit in this part and to see which is the numbers or points where you consider an interesting interval for describe the likelihood uncertainty. This is the likelihood interval, the definition of likelihood interval, based on to fix a likelihood value. I don't know if it's too much use, okay, but you can see the idea is good. Okay, some detail. This is a strong detail because it's based on to measure uncertainty, and in this course, I think it's not possible to talk much about that. But very quickly, you can see this idea that this expression is very close for several points. Is based in the second derivative in the point, no? You can see that if I compute the second derivative of the log likelihood function in the point, in the maximum likelihood maximum likelihood estimation, no? This point is the maximum likelihood estimation, in our case, 2.11. If I compute the second derivative, then this value is going to produce some measure of this interval. And really, the confidence interval that you know maybe from an initial course of statistics, this idea of confidence interval is based on the second derivative, exactly, of the log likelihood function. Okay. I am not going to show more details. This one is another example. Okay. Yes, I want to show this example. It's only an example. Based on the previous model, exponential model, you remember I showed the results with the moments, and now I show the likelihood as another method. But if you compute with likelihood, you are going to obtain the same. You remember this is a result when you consider moments. And now with likelihood, the result is the same. This is not necessary. This is an example when the moments and likelihood produce the same result for the punctual estimation of the parameter, but it's not in general. Okay, it's very important to fix that. In general, likelihood is the best method because in a regular case show strong properties like I was explaining, consistency, sufficiency, and etc. But moments is more easy. The method of moments is very easy, very quick, and many times when you want to compute this one, because in this case you only need to do the derivative, and it's easy to describe the result. But in general, likelihood can be very strong problem of optimization, and many times you need a seed. And typical procedure is to use moments as a seed for likelihood estimation. Okay. Okay, this is the idea that when theta is not a number, when you fix as a vector, no? Take into account that this score function, when you have two derivatives respect from each parameter, is a vector, no? Because you are going to do the log likelihood function derived by the first one, is the derivative from the last one. For instance, in this example, or in this notation, where I put 1 from P, no? Okay, where theta is a vector of parameters with P. And then take into account that score function is a vector, is a score vector, and the second derivative is a matrix, and is we call matrix information of Fisher. These matrices are going to produce this uncertainty. Remember that I comment that with this matrix we can compute the intervals. Okay, maybe let me to show. Okay. I am going to come back, okay? I am going to come back, but sorry, because I don't want to do this one. Maybe I want to show some detail because I am not going to explain, but I think it's interesting in this moment to comment. Because I want to start with another example, but here. Because this one is a summary. This is the same slide than previously, but in here is a summary that I was explaining with strong details that for future part. Okay. Today you can see we see moments and likelihood, and I explained that these ones are going to produce a measure for a way to compute punctual estimations, no? And interval estimation, when you want to fix an interval estimation, I showed this idea that we can base in likelihood method using the second derivative or the matrix, the Hessiana, okay, of the function. Then this one, and more details on that I am not going to explain. Then let me to show this slide when it's a summary of every that I was explaining on likelihood. And moreover, the idea for could consider intervals, okay? This one is the same than previously with some strong details. You can see this one is a practical slide. You have a sample, summarized. You can describe a function from theta, given a sample. Log likelihood, remember, is to consider a logarithm of this function. Theta is a punctual estimation, and it's obtained to maximize the log likelihood function. Score function is important, is the partial derivative of log likelihood from each parameter. And when to put equal 0, you obtain this punctual estimation. And remember that this punctual estimation is a vector in this case. Important detail is to obtain, you can see this row, say from here you are going to obtain theta hat. But of course, not necessarily theta hat is obtained from 2 equals 0. Of course, many of you know more mathematics. With a strong mathematician approach, you know that not always the maximum holds in the interior of the domain. And maybe strong properties you need on the function in order to assess that you are going to obtain this theta hat doing a score function equal to 0. But let me to say that in a regular case, in a general case with properties, you can obtain it. But if you want an easy example where it's not going to hold, you can take uniform distribution. Uniform distribution, if you write as a model, then is a counterexample, easy, where you can see that maximum likelihood estimation is not obtained doing the natural procedure of derivative and equal to 0. Okay, but in the general case, when you can do it, and I am going to in the last class I explained why I am sure that in the many times you can use this one. Okay, because it is a very large family.
Isabel, what happened if it's at the extremity of the interval? Can it happen that it's not in the middle, but is one of the?
In here.
If it
Which
happens
interval?
that the maximum value is not the one that is not the local minimum, but is at the extreme.
No, the example is in uniform. Uniform distribution is easy because you can write uniform. You can see my blackboard. I can write. Let me know. You can see.
No, we cannot see it. Just 1 second. Try to.
Okay.
Yeah. We can see.
Yes. You can see.
No, can you write higher because it's lower? We don't see. Yes.
Yeah. In this case, when you consider 0 from 2 theta, for instance, then you know it's a random variable, no? That the values, this is the density. It's the equal density in an interval from 0 to theta continuous. Then in this case, when you want to compute this one using maximum likelihood estimation, it's easy, very easy exercise where you can understand why no necessary is a local minimum, maximum. Okay. It's very easy example, but these are typical from me. For a professor, it's easy because in an exam, if you want everybody have some problem. Okay, and this case, in this summary, I want to say this one you need to obtain, but in general case, with strong properties on densities, you can obtain as a minimum, as a maximum from two derivative of the log likelihood, and the second derivative from as a matrix, no? When is evaluated in the maximum likelihood estimation, okay? And moreover, when you compute, you can see disappear the sample because this one corresponds to compute from this expression the expectation. And then when you compute the expectation of this one, then this matrix are going to produce some numbers that measure the standard error of the estimation. Okay, then for instance, theta 1, the first one, will be close. Let me to put close because more exactly is exactly to compute using the matrix, but some approximation is theta 1 is exactly, is approximated living in this interval. The punctual estimation that you obtain with the method plus minus 2 times square of this number. And for the second parameters, I am going to take this number. And it is same. Here only 2 dimensions because it's enough in order to understand the idea. But the most important is to remark this one that you are going to compute theta. And from theoretical point of view, you want to develop this one as an interval, you need to write the expected value, okay? But with numbers, you don't need to do it. You can really put directly. And this is the idea of standard error that you can compute in general when you have maximum likelihood estimation. Remark that 2, this number 2, is from Gaussian distribution because we are considering in here asymptotically normally. We consider that this estimator is asymptotically normal. Then I can compute the uncertainty using normal distribution. Then 2 is the critical value in 5% of risk in Gaussian. Is an approximation too. But this one is some receipt for practical point of view. But remark that several theorems you need to arrive to this expression, okay? Because first one, which is conditions on the density in order to get this score function as a good approach to compute maximum likelihood estimation. Secondly, you need strong results based on to write the variance or the uncertainty of the parameter based on this second derivative. Another important result is based on these properties of the property of asymptotically normal that you need to write this one. And moreover, that in this slide is not shown, is to talk on the efficiency of this estimation. Because the strong properties that you need on this family in order to obtain this beautiful approach ensure that this estimator are going to be efficiency. Efficiency is the best, really the best type of estimator, depending on the situation, but in general, when you need to most important properties. When you estimate a parameter, you want that the first one from theoretical point of view. From theoretical point of view, I want to say that I say x1, xn is a sample, but for me, it's a theoretical point of view, are different independence and identically distributed. Then theta, this one, is obtained as a random variable, and that I want is the expectation of this one is exactly theta that I want to obtain. No? And the second one is from theta hat from random variable, from probability point of view, thinking on this theoretical approach. I want that the variance is minimum, no? Because I am thinking my idea is given a sample n, and suppose that I have several options to fit theta, I want the best for me is with minimum variance, such that are going to say, okay, with n information, the dispersion, in some sense, of the result is minimum, okay? BH is related with expectation, and efficiency is related with variance. These are two main properties on estimators. And I can talk again with a lot of details on estimation, but in this small course, I cannot read. But let me know if you want to know more details. And I think if you want, I propose the next day, you can use your computer. I don't know what you prefer. For me, to take this one, you can see my screen. This is a console app.
Yes, yes, we can see.
For me, it's okay. You can consider different RStudio or I don't know, but the minimum one is this one, okay? And then I am going to show you some procedures from modeling, okay? That I was explaining, but from practical point of view. But I think it's more, sorry, I think it's interesting that you can obtain and to try to do the same that I do, okay? Not only because I think it's like a practice, okay? I think my experience with virtual class is not very good when I want to try to do a practice, but we can try. And if you are prepared, only you need to be installing your computer, okay? It's enough. And then I am going to show some details and start to talk on modeling, okay, with several variables. Then this is a small example that I am going to show, but I want to talk on linear regression and different models. I try to do some tree and neural network, okay?
You can send the data so they will have it and they can practice. You can send this.
Okay. Now I am going to do it, yes, now, okay? Okay.
For the next
for
class,
me,
because
yes.
yeah.
Yes. I am going to send an email with the data, okay, for the next class.
Quem sabe usar ela ensina o outro, mostra os outros como usar.
No?
Yes, they will do in pairs. They will do in pairs next class.
Vale. Okay, because really, I think it's interesting to talk on different models, but you can see, for me, with only 4
Python,
classes,
they can use it Python also or only R?
Python, if somebody use Python, no problem. No.
No problem.
No, really, that I want to show is to talk on, because now we only talk about some small details from probability, and to translate to the main approach from statistics. And you can see the summary is too emphasis in estimator, the law of estimator, and some properties, and not too much details. Then the next day we start with univariate case, very quick with the details with numbers that I was explaining, and then with several dimensions, with 2 dimensions, linear regression, and I am going to show with several dimensions, okay?
Okay. So,
okay,
thank you. If you can send us some references so they can read in the meantime. Some.
Okay.
Thank you very much.
Thank you.
So let's take Isabella.
Okay. Thank you. See you.
Thank you. So see you next Thursday. Thank you, Isabella.
Thank you.
Bye-bye. Bye-bye. Bye-bye, Glaston. Bye.
Bye. Bye.